Welcome to this deep dive. Today, we're aiming our metaphorical telescopes, I guess, at some of the universe's most perplexing objects, black holes.
Definitely perplexing. And we've gathered some, really recent news stories, including some findings just out in a new scientific paper. They offer some, fresh and sometimes quite surprising glimpses into these things.
Right. So our mission for you today is to try and unpack what these specific findings are telling us about black holes, maybe their unexpected impacts sometimes on the universe around them, and just how much we still have to figure out.
Yeah, that last point is key. There's still so much unknown.
Okay, let's get into it then. Because this first story, it involves a satellite, a really massive black hole, and, well, it has kind of a sad ending, unfortunately.
It does, yeah. Back on February 17th, just this year, the Japanese Aerospace Exploration Agency, JAXA, they'll launch this really ambitious satellite. It's called Hitomi.
Hitomi, right.
And its whole purpose was basically to be an astronomical observatory up in space, specifically designed to capture X-rays.
Which we can't really see from down here on Earth, can we? The atmosphere gets in the way.
Exactly. The atmosphere blocks them, so you need to go to space. And the goals were huge. They wanted to study what happens right around black holes, get info on how huge things like galaxy clusters form.
Yeah.
Basically use X-rays to chip away at some really big cosmic mysteries.
A major undertaking. Must have cost a fair bit.
Oh, yeah. About $273 million, a significant investment. But here's the sad part. Only about a month after it launched.
A month? That's it?
Yeah, just about a month. A really unfortunate mix of, it seems, human error and software problems caused it to start tumbling out of control. And, well, it was lost. A real blow.
Oh, it's awful. All that potential.
Oh.
But hang on, the story doesn't quite end there, does it? Because even though its mission was cut so short, right before it, went silent.
It managed to send back one last image, one final piece of data.
And that's what this new paper in Nature is all about.
Precisely. That last look was aimed at the Perseus cluster. Now, this is one of the closest really massive galaxy clusters to us, about 240 million light years away, give or take.
Okay, and it's known for having a particularly big black hole at its center.
A monster, yeah. A supermassive black hole right in the heart of this huge cluster of galaxies.
And Hitomi measured what exactly?
It measured the X-ray activity coming from the incredibly hot gases right there in the core of the Perseus cluster. And the thing is, it did this with unprecedented precision, like 50 times better than any instrument had managed before.
50 times? Wow, that's a leap.
A huge leap. And that precision was crucial because researchers had, pretty strong ideas about what they should find there.
Which was lots of chaos.
Exactly. They expected these incredibly hot, dense gases swirling around that central black hole to be really turbulent, chaotic, moving incredibly fast.
And why did they expect that? Just because of the black hole itself?
Well, partly the black hole, but also because these giant galaxy clusters, they contain just enormous amounts of mass, not just stars and gas you can see, but also huge quantities of dark matter.
Right. The mysterious dark matter.
Yeah, and the combined gravity of everything, the galaxies, the gas, the dark matter, the black hole, was expected to really stir up those hot gases, whipping them into a frenzy.
Okay, so chaotic, fast-moving gas was the prediction. But the surprise from Hitomi's last look was...
The surprise was, it wasn't like that at all. What Hitomi's super precise measurement showed was that the hot gases were actually moving much, much slower than expected. It was remarkably quite a calm environment right there at the cluster's heart.
Wait, calm. Next to a supermassive black hole in a giant cluster. That sounds wrong. Why is that finding so significant?
Well, it's significant for a couple of reasons. On one level, it helps scientists pin down some fundamental numbers about the universe, parameters of cosmology, and how these huge structures actually grow over billions of years.
Okay, so refining the big picture.
Right. But the really fascinating insight, and one of the co-authors, Brian McNamara from the University of Waterloo, really highlighted this. The insight comes from what that calmness tells us about the black hole's influence.
Didn't he have a quote about that gas being like, the stuff of the future?
Yes, that's the one. He pointed out that this hot gas Hitomi observed is the basic material, the feedstock, from which future galaxies will eventually form.
The raw ingredients.
Exactly. And interestingly, there's actually way more of this hot intergalactic gas out there between galaxies than there are stars inside galaxies. Most of the universe's normal matter, its building material, never actually made it into a galaxy.
Okay, so if this gas is future galaxies, and it's unexpectedly calm, what does that imply? I think you'd want turbulence to get things started.
Oh, but see, that's the key. The calmness suggests something profound about the black hole's energy output. These supermassive black holes, they don't just suck things in, they also blast out enormous amounts of energy.
Right, jets and radiation.
Exactly. And this calmness indicates that the energy being pumped out by that central black hole is being absorbed very, very efficiently by the surrounding gas. It's basically heating the gas up.
And stopping it from cooling down and collapsing to form new stars.
Precisely. It keeps the gas hot and spread out. So the big takeaway from Hitomi's final observation is that these black holes are acting like incredibly effective cosmic thermostats. They're actively controlling how fast their host galaxies can grow by managing this reservoir of potential star-forming gas.
So the black hole is basically putting a brake on galaxy growth.
It's putting a ceiling on it, yeah. By keeping that gas hot, it limits the supply of cold gas needed for making stars.
Wow. So even though the satellite was lost so quickly, that one snapshot provided, as the source says, huge information, a really significant insight into how black holes shape galaxies.
Absolutely huge. And, it also really underlines how much we don't know. We make predictions based on our models, and then an observation like this comes along and shows us nature's doing something a bit different, something more efficient, maybe.
It really drives home the mystery, doesn't it? They just keep surprising us. But we do know they do one thing pretty reliably, which leads nicely into our next story.
They eat stars.
They definitely eat stars. And this second source is about watching that happen, or, well, seeing the aftermath very clearly.
Yeah, more the immediate aftermath. This involved using the European VLBI network.
The VLBI. That's where they link up radio telescopes across, like, continents, right? To make a virtual telescope the size of the Earth.
That's the one. An incredible technique. And using this massive virtual telescope, researchers managed for the very first time to get an incredibly sharp close-up view of a jet of particles being blasted out from a supermassive black hole at speeds approaching the speed of light.
Okay, hold on. Blasted out. How does stuff get blasted out of a black hole? I thought their whole deal was pulling stuff in.
It's one of the most mind-bending parts of black hole physics. So when a star gets too close, the black hole's immense gravity shreds it apart. Tidal disruption, they call it.
Ripped to shreds. Got it.
But not all of that star stuff falls straight in. A lot of it forms this swirling pancake of gas around the black hole and accretion disk. It gets incredibly hot and bright as it spirals inwards.
Okay, the disk is like the waiting room before falling in.
Kind of, yeah. But crucially, some of that material from the star, instead of falling past the point of no return, the event horizon gets caught up in powerful magnetic fields near a black hole's poles, and these fields act like channels.
Funneling the material.
Exactly, funneling it and then ejecting it outwards in these really narrow, incredibly energetic beams. These are the relativistic jets. We've known about jets for a while, but seeing one fire up right after a star gets eaten, that specific type of event, linking the tidal disruption to the jet launch, that's relatively new territory, only really confirmed in the last 5 years or so.
And this particular cosmic fire hose, where did they see it?
This was coming from a supermassive black hole way out in the Draco constellation, and it's distant about 3.9 billion light years away.
3.9 billion light years. And they got a close-up view. How close are we talking?
Well, the source describes the apparent size of the jet they resolved as being like a 2-year-old coin viewed from that distance, which sounds tiny, but for something nearly 4 billion light years off, resolving something that small.
That's unbelievably sharp imaging.
It really is. It represents some of the most precise measurements ever made with radio telescopes. It let them see right down near the base where the jet is actually launched.
So getting that clearer picture, right as the jet forms after a star meal, that must be a huge step forward in understanding how these jets work.
Absolutely. And Stephanie Camosa, one of the astronomers involved from the Max Planck Institute for Radio Astronomy, she mentioned that this is just the beginning. With the next generation of even more powerful radio telescopes coming online,
They'll see even more detail.
that's the hope. She thinks they'll reveal much more about that chaotic process of the star being consumed and, critically, how these incredibly powerful jets actually form and evolve right there in that extreme environment just outside the event horizon.
Okay, so pulling these two stories together. One shows a black hole acting like a surprisingly calm, large-scale regulator of galaxy growth.
And the other shows this incredible violent power up close, shredding a star and launching a particle beam near the speed of light.
It feels like they underline the central point, don't they? Which is
Just how mysterious these objects fundamentally are. Both observations give us new, concrete data, things we didn't know for sure before. But they also really highlight that black holes are still one of the least understood things in the entire universe. As the sources basically say, we know almost nothing about them on a deep level.
It really feels that way sometimes. They still sound like pure science fiction half the time. The sources even touch on some of the really wild ideas floating around, precisely because our understanding is so limited.
Totally. Like the whole concept that their gravity is so intense it can literally slow down time. You know, the stuff you see in movies like Interstellar, that's based on real physics predictions.
Or that completely mind-bending idea that maybe every black hole contains an entire universe within it.
Which, if true, leads to the slightly dizzying thought that maybe we're inside a black hole right now.
Doesn't bear thinking about too much. And then there's the defining feature, right? Their gravity being so strong that once you cross that boundary, the event horizon.
Not even light can get out. The cosmic speed limit isn't fast enough.
And didn't the source mention Stephen Hawking's later idea about them potentially being portals?
Yeah, his speculative idea that maybe black holes aren't complete dead ends, but could be gateways to another universe. It's important to stress that's a theoretical idea, but the speaker in our source material found it compelling.
And it just goes to show, right? We have these amazing mathematical descriptions, these wild theoretical possibilities, but fundamentally,
We don't really know what happens inside. We don't have a definitive answer to what a black hole is at its core, beyond its observable gravitational effects on things around it.
it makes you understand why some people, looking at this profound lack of direct knowledge about the interior, almost referred them as, what was the phrase? The ghost of the universe.
It's a good description in a way. Their presence is felt profoundly, but their true nature remains hidden. And these studies, like Hitomi's Last Glimpse or the VLBI's Sharp Jet Image,
Like precious clues gathered from the edge of the abyss.
exactly, they push our technology and our understanding right to the limits. We get these concrete data points, unexpected calmness here, incredible jet power there, where before we might have only had theory.
But at the same time, they just seem to emphasize how much is still locked away behind that event horizon. We're seeing the effects, the influence around them.
But the central object itself, what it truly is, still one of physics' deepest, most compelling mysteries.
And that really brings us back to these fundamental, almost childlike questions that make black holes so fascinating and keep scientists pushing for these incredibly difficult observations.
Yeah, and speaking of fundamental questions, one thought from our source material really sticks with you. It perfectly captures the level of basic mystery we're still grappling with. It's something to leave you pondering. When a black hole eats a star, does it poo it out anywhere?
Provocative indeed.
Hmm.
A simple question, but one that cuts right to the heart of what we don't know. Something to think about, definitely, as you consider these incredible, mysterious objects shaping our universe.